I'd like to show you something else on this problem. I made it a separate video because the last video was getting long, and also this is kind of a side point, which is has to do with choosing the axis of rotation in a problem like this. I solved this problem in previous video, and the way I did it was placing the axis of rotation at the location of the support. I want to show you now that you get the same answer, even if you place your axis of rotation in a different spot. So I'm going to solve exactly the same problem that I was solving. The F equals MA problem is exactly the same. Only difference this time is I decide, instead of placing the axis at the support, I'm going to place the axis of rotation there at the end of the rod. Which again, might seem a little bit weird intuitively, because why would the rod rotate about that point? And the answer is it wouldn't, but the reason it wouldn't is because the equation I'm about to write is true, because it's in static equilibrium about that point. That's why it wouldn't rotate about that point. So if something's in static equilibrium, it has to be in static equilibrium about every axis of rotation, or else it won't work. So as a result, you can pick the axis of rotation to be whatever you want. So anyways, let's try solving it this way. So all of your torques are going to be different this time. That's the first thing to realize, because torque depends where your axis of rotation is located. So this time, torque 2 is actually equal to 0, but the torque from the normal force is not equal to 0. Let's do the signs first. The normal force is going to exert a torque up like this, so that'll be positive. This one is going to be clockwise, that's negative, and this guy's going to be clockwise, that's negative. So we've got torque from the normal force positive, torque S negative, torque 1 negative. And remember that when I write down these L values, I have to measure my L values from the location of the axis of rotation all the time. So the first L value for torque N is going to be this distance here from the axis to the support. That's X. The second one is going to be from the axis to the center of the rod. That's 0.5. The third one is going to be from the axis of rotation to the end of the rod. That's going to be 1. That's meter. Okay, so actually, what was probably the trickiest part of the previous problem is gone. The L values are actually much easier to measure this way. The downside is we have the normal force appearing in the torque equation this time. So you have to solve, last time we didn't use this result of what the normal force was. This time we actually need to use that result from the F equals MA equation. But we solved for it, so it's no big deal. So now I want to say the sum of my torques equals 0. So we're going to have Fnx minus 0.5 msg minus 1 times m1g equals 0. Now notice this time we cannot divide out a factor of g, because not every term has a g in it. So we're going to get, let's just plug everything in. The normal force is 4.41 from, that number is coming from the F equals MA equation, which we solved in the previous video. And then we're going to have 0.5, ms is 0.15 times 9.8. And the third term is going to be m1 is 0.1 times 9.8. And that equals 0. So that is 4.41x. 4.41x minus 0.5 times 0.15 times 9.8. And then minus 0.1 times 9.8. So this number turns out to be, oops, put it in backwards. One moment. There we go. 1.715. So then that means x equals 1.715 divide 4.41, and that gives me 0.39. So we get the same answer no matter what we use for the axis of rotation. Sometimes the algebra can look very, very different depending on where you pick the axis of rotation. It might make the problem easier or harder, but it's solvable no matter where you put the axis of rotation. And in fact, you could even put the axis of rotation in two different spots and create a system of equations that way if you were so inclined. But I won't show any examples of doing that. You should understand how to place the axis of rotation at different locations at will. I could ask you to place the axis of rotation at a specific point, or I might just say put the axis of rotation wherever you want. Well, I won't actually say that, but if I don't force you to put the axis at a certain location, it'll be up to you to choose whatever you think is the best axis of rotation. But the first thing is to realize, number one, that you need to pick an axis of rotation in order to calculate torques. And number two, to realize that in a static equilibrium problem, you can pick that axis to be wherever you want.